Hello and welcome to Tribe Topper. I'm Sonal Gupta, and this channel is about increasing your understanding of physics. To clear your concepts, subscribe to our channel and click the bell icon for latest updated videos. This video session, you're going to learn about the emission spectrum of a black body. See, in the previous video, we discussed that when a black body becomes enough hot, it starts emitting radiations. So, though there might be some predominant color corresponding to a particular temperature, but that does not mean that only one wavelength will emerge out. So, depending on the temperature, using an instrument called spectrometer, the intensity of the radiations is measured corresponding to a particular wavelength, and intensity is defined as the power emitted per unit area. So the intensity of the radiation coming out of a black body is measured with a spectrometer, and it is power over area. A typical wavelength graph that you can see here is shown in this picture. So this is for a black body at a temperature somewhere close to 6000 Kelvin, which is almost the temperature of the sun, and where of course we are assuming that sun is on a near perfect black body radiator. So let's discuss the characteristics of this particular graph. There is a peak value at about 500 nanometers. If I take a close approximation to a round figure, around 500 nanometers, this is the highest peak, that peak value, which actually this 500 nanometers correspond to the green and blue light. Then there are significant radiations at all visible wavelengths. So you will have the visible wavelengths and there will be enough wave radiations in that range. And there is a steep rise from zero intensity. If you see here, relative intensity and corresponding to the wavelength, there's a sharp rise here in the intensity starting from zero. And the line does not touch the origin. If you will actually enlarge the graph is not passing through the origin. It is already starting up a little above zero. And as you see, we go to the right at larger wavelengths, which is beyond the peak of the curve, then the intensity falls to the low levels and approaches zero asymptotically. So there is a certain wavelength corresponding to which you have a very high intensity, and that is at a particular temperature. You can get different peaks for different temperatures. These peaks keep on shifting to the left. Like if you have a little lower temperature, this peak would have been a little right here, towards right. As the temperature goes on increasing, the peaks keep on shifting to the left. So that's how a graph uh, tells us the variation in the intensities corresponding to the wavelength for a particular temperature of the black body. Another important thing which talks about the wavelengths and the intensity is the Wien's displacement law. So this law actually tells us that the shape of the graph depends on temperature. He showed that the height of the curve and the overall width depends on the temperature alone. So what is the statement of the Wien's displacement law? It states that the wavelength at which the intensity is a maximum is related to the absolute temperature of the black body by this relation, that lambda max is equal to B times T. So actually it was that lambda max is proportional to T, that is the wavelength at which the intensity is a maximum, means the wavelength corresponding to a maximum intensity, we denote it as lambda max. It's directly proportional to the temperature of the body. Higher the temperature of the body, higher will be the intensity for a maximum intensity for a wavelength. So when you remove the proportionality sign, you get a constant here. So lambda max is equal to Bt, where B is the Wien's displacement constant and T is the temperature of that hot black body emitting the radiations. So that's all in this video session, where you learned that how the intensity depends on the temperature or what colors of wavelengths are emitted by black body radiators. In the next video session, you are going to learn about the absolute temperature and the dependence of the power radiated by the body. Thank you.